At this exact moment, thousands of miles above us, the global economy relies on a single piece of thermodynamic wizardry: the high-bypass turbofan engine. For decades, the formula was simple: make the fan at the front bigger, force more air around the core and burn less fuel. But in the aviation industry, you eventually hit a thermodynamic wall. This is not Rolls-Royce motor cars. There are no hand-stitched leather seats or luxury chassis here. This is Rolls-Royce plc, pronounced PLC, an independent aerospace and defense titan responsible for powering over 35 types or commercial aircraft military fleets worldwide. And they are currently running a multi-billion-dollar gamble to break through that thermodynamic wall. To understand the scale of what they are attempting, look at this power gearbox. It manages 64 megawatts of power. That is equivalent to the power output of an entire small city, or roughly 85 Formula One cars running simultaneously packed into a component the size of a carry-on suitcase. If it fails, the future of sustainable aviation stalls. If it succeeds, it changes flight forever. Welcome to the deep dive inside Rolls-Royce PLP's most ambitious masterwork. Over the next 20 minutes, we will unpack the blueprints of the UltraFan, the world's largest aviation engine demonstration program. We will step inside Testbed 80, a facility so technologically advanced it captures 10,000 parameters of data every single second. And we will look at how an engineering icon is utilizing data, sustainable aviation fuels, and architectural disruption to survive the next century of propulsion. Let's get into the mechanics. #Spanner Act 1, the UltraFan Revolution. To appreciate why the UltraFan is a radical departure for Rolls-Royce, we have to look at how conventional jet engines work. For 30 years, Rolls-Royce built its reputation on the three-shaft architecture of the Trent engine series. In a traditional direct drive engine, the massive fan at the front is connected via a solid shaft directly to the low-pressure turbine at the back. When the turbine spins, the fan spins at the exact same rotational speed. Here lies the engineering paradox. Big fans are highly efficient, but they want to spin slowly to prevent their outer blade tips from breaking the sound barrier and generating destructive shock waves. Turbines, conversely, are highly efficient only when they spin incredibly fast. In a direct drive setup, you are trapped in a compromise. The fan spins too fast for maximum efficiency, and the turbine spins too slowly. The UltraFan breaks this compromise by introducing a power gearbox between the turbine and the fan. This allows the low-pressure turbine to run at ultra-high speeds for peak thermodynamic efficiency, while the massive 140-inch front fan turns slowly, quietly, and optimally. This isn't just an evolutionary step. It's a complete architectural reset for a company that built its empire on direct drive systems. This design pivot yields staggering metrics. Compared to the first-generation Trent engines, the UltraFan delivers a 25% improvement in fuel burn efficiency. In an industry where airlines operate on razor-thin margins and carbon taxes are rising globally, a 25% jump is astronomical leap forward. Boot building a gearbox that can transfer 64 megawatts of power without melting under its own thermal energy requires a complete material science overhaul. Look at these fan blades. Traditional titanium blades are heavy. If you scale them up to a 140-inch diameter, the centrifugal force would literally tear the engine roots apart. Rolls-Royce's solution: carbon titanium composite blades. Woven from hundreds of layers of high-strength carbon fiber, pre-impregnated with resin, and shielded by a micro-engineered titanium leading edge. This slashes the weight of a twin-engine aircraft by up to 1,500 pounds, equivalent to removing an entire cabin section of passengers. Inside the core, the story gets hotter. The UltraFan runs at unprecedented temperatures to squeeze every last drop of energy out of the fuel. The temperatures exceed the melting point of standard nickel-based superalloys. To survive, Rolls-Royce implemented ceramic matrix composites, or CMCs. Thus, materials are one-third the weight of metal but can endure temperatures that would instantly deform conventional aerospace hardware. Combined with a high-pressure ratio core, The system acts as a highly concentrated heat engine maximizing propulsion with absolute material minimization. Building construction, Act 2 Testbed 80. The data engine you cannot fly an unproven architecture. To test an engine or the scale and complexity, you need an equally monumental piece or infrastructure. Enter Testbed 80, the largest and most advanced indoor aerospace testing facility on Earth. Covering an internal footprint larger than a premier football pitch, this indoor complex was engineered specifically to handle engines pushing up to 155,000 pounds of thrust. Before Testbed 80, engine testing was often a fragmented process. Data points were sampled intermittently, and physical examinations required halting tests and stripping components down. Testbed 80 treats the engine as a living digital organism. Every single test run captures data across more than 10,000 parameters simultaneously. Sensors measure pressure, structural vibration, acoustic resonance, and thermal gradients at a sampling frequency of thousands of times per second. This isn't just about collecting raw data, it's about creation of a real-time digital twin. As the physical engine screams at full throttle inside the reinforced concrete chamber, a precise virtual model mirrors its behavior in the cloud. Using advanced cloud analytics, engineers can cross-reference physical stress with virtual predictions instantly. This allows Rolls-Royce to predict component wear, understand structural fatigue, and catch microscopic anomalies before they turn into real-world mechanical failures. One of Testbed 80's most formidable capabilities is its non-intrusive energy X-ray imaging array. This system allows engineers to look directly through the solid metallic and composite casings while the engine is running at full load. They can monitor the exact clearances between the spinning turbine blades and the inner engine wall down to a fraction of a millimeter. In the past, analyzing these clearances required complex math and post-test inspections. Now they can watch it happen live at 10,000 RPM. Pronounce RPM. The infrastructure hidden beneath the floorboards is just as complex. Testbed 80 houses a dedicated 130,000-liter underground fuel storage system designed to seamlessly manage multiple fuel profiles, including specialized aerospace blends and sustainable aviation fuels. The facility can cycle through different fuel types mid-test without disrupting the engine's operational sequence. This flexible piping infrastructure is vital for the company's next major pillar, proving that massive engines do not require fossil fuels to deliver maximum performance. #Seedling, Act 3, Decarbonizing the Skies. The aviation industry is facing its biggest challenge yet, achieving net zero carbon emissions by 2050. For a company whose primary product burns hydrocarbons at high altitudes, this is an existential hurdle. The UltraFan architecture solves the efficiency side of the equation by using 25% less fuel. But to truly decarbonize, the fuel itself must change. This is where Rolls-Royce's total commitment to 100% 100% sustainable aviation fuel or SAF, pronounce SAF, comes into play. Current international regulations only allow commercial engines to run on a maximum blend of 50% SAF mixed with conventional, fossil-derived Jet A1. Rolls-Royce has spent the last few years systematically proving that their current production engines, including the entire Trent family and the new UltraFan, can operate with absolute safety on 100% unblended SAF. SAF derived from waste oils and agricultural byproducts drops net life cycle CO2 emissions by up to 80%. But SAF is a transitional solution. The real endgame requires exploring entirely new power sources. For smaller, regional flights, Rolls-Royce is developing advanced hybrid electric and microgrid propulsion networks. But for long-haul wide-body aircraft, batteries are simply too heavy. The long-term alternative is hydrogen. Hydrogen possesses an energy density by mass that is nearly 3 times higher than conventional jet fuel, and its only byproduct is water vapor. In partnership with major airlines like EasyJet, Rolls-Royce has already run successful ground tests of a modified gas turbine engine running purely on green hydrogen. The engineering challenges are immense. Hydrogen must be stored cryogenically as a liquid at minus 253 degrees Celsius inside the aircraft, requiring completely redesigned fuel tanks and combustion systems. This technology is decades away from widespread commercial deployment, meaning the immediate future relies on squeezing every ounce of data out of the engines currently flying today. This brings us to the operational reality of Rolls-Royce plc. Their maintenance, repair, and overhaul or MRO, pronounce MRO, network. Through their pioneering Total Care service packages, Rolls-Royce doesn't just sell an engine, they rent power by the flying hour. Thousands of engines currently in service send operational health data directly to global monitoring centers via satellite links while airborne. By applying predictive machine learning to this massive incoming data stream, they can schedule preventative maintenance precisely when an aircraft lands, preventing costly delays and optimizing fleet efficiency across the globe. Hashtag chart with upwards trend, outro and call to action. From inventing the legendary Merlin engine that powered historic aircraft, to pioneering the three-shaft Trent series, and now running the world's largest geared turbofan demonstrator, Rolls-Royce plc continues to redefine the boundaries of engineering. The UltraFan program and testbed 80 are more than corporate milestones, they are the foundational building blocks for a cleaner, faster, and more connected world. If you want to look closer at the mechanics of these propulsion systems, check out the official Rolls-Royce Discover Engines application, where you can interact with fully detailed 3D exploded views of these power systems. Make sure to subscribe to the channel to track the next phase or the UltraFan's full power testing milestones. Let us know in the comments. Do you think geared architectures or hydrogen combustion will ultimately win the race to net zero flight? Thank you for watching, and we will see you in the next deep dive.